Hello, my name is Yanxun Zhu, and my project topic is the emotion recognition through physiological signal. This is my outline. First is the introduction and the background of the problem I want to solve, and next is the description of my project. I will introduce the database I used and the emotional model, the preprocessing, like how I denoise my signal. In this project, I propose two different kind of feature extraction, the functional-based feature and the signal-based feature. And the machine learning approach I used in this project. And after the experiment, I will evaluate my work and make a summary. In the end of the presentation is a demonstration of my project. In the modern age, the development of the technology becomes faster and faster. As a result, computers and machines are more and more important in our lives because we rely on them much more than before. If machines can read and understand human emotions, not only the efficiency can be improved, but also we can get a better response when we interact with computers and machines. That is the improvement of human-computer interface. However, there are so many problems. Most studies of emotion recognition are using facial images or audio signals to do the research. But I think the physiological signal is also a very good way, especially for the people who has a poker face or they tend to suppress their voice. In this situation, the facial images and the audio signals may not be very useful. And also physiological can truly reflect our emotion. Like if we are very exciting, our heartbeat will be faster and the blood pressure will be higher. And most of the researchers who use the HRV series to extract the features for the ECG signal, and I want to use another way to extract the features. Finally, the individual differences is always a very big challenge when we deal with physiological signals because the body conditions is vary people one by one. For some people, they may have a faster heartbeat than others, and I want to eliminate this kind of problem. Well, I use the Dreamer database. It is a multi-model database with EEG and ECG signals. Here I only use ECG signal because it will be more practical. ECG signal is very easy to measure. Like we can use our smartphone, even smartwatch, to get the ECG signal. But if we want to get the EEG signal, it will be very difficult. We have to wear a device on our head and the signal is very weak with a lot of noise. There are totally 23 participants in this database, and each person watched 18 video chips and recorded the 5-level variance, 5-level arousal, and 5-level dominance as label. Here I only use the variance and arousal label. And because of my feature extraction, I kick out three subjects as outlier, so I only use 20 participants in this database. For the emotional model, I use the variance arousal model. This model sees emotions as the combination of different levels and different dimensions. Variance is the positive of the emotion. For example, sadness is the low variance and happiness is high variance. Arousal is the activation of the emotion. For example, anger is high arousal and sadness is the low arousal. Here I separate each dimension into two levels, just high and low. When we get a signal, the first thing we have to do is to denoise. Here I applied a A-level discrete Waverly transform to filter out the frequency that is higher than 64 Hz and lower than 1 Hz. They may be the signals from our muscle. The high frequency part may be the signal from our muscle, and the low frequency part may be the motion artifact, and they are the noise we don't want to have in our signal. The picture is before and after denoise. We can see that the baseline become very flat. after denoise, and it will be very helpful if we want to extract the peak. Next, after denoise, next we have to detect the peak. We call the R peak. This R peak for each heartbeat. Here I just set the different window size and the threshold to detect it, and the picture is a result of the R peak detection. With this, we can compute the R interval. That is the interval between each two R peak, and it is a very useful indicator when we deal with the ECG signals. Now we have the R intervals, and we can use it to extract the ECG feature. Most of the studies with ECG signal use HRV series or other nonlinear methods to extract the features, and I call this kind of features the feature-based features, because it uses a function-based feature, because it uses a function and it calculate the feature by a function or an equation, and use a computational number to represent the whole signal. Here I extract totally 17 features by the functional based feature. And for the HRV time domain, I calculate the mean and standard deviation and the root mean square of the R interval. And it is very popular, very commonly used when we compute the HRV series features. And for the frequency domain, first we compute the power of the R intervals and then get the power in the specific bandwidth. These features have some physiological meaning. For example, in the low frequency band power, within 0.04 Hz to 0.15 Hz is the index of sympathetic activity, and the power within 0.15 Hz to 0.4 Hz is the index of parasympathetic activity. This kind of feature is not only used when we do the emotion recognition, but also when we do the research about heart disease diagnosis. These kind of features are very commonly used on that kind of research. Yes. And this is the power spectrum of the R interval. For nonlinear methods, I use Puncare plot and DFA. Puncare plot is that we set the x-axis is the R interval and the y-axis is the next R interval, and we can get an ellipse of the picture and calculate the two axes of the ellipse. And for the DFA, I calculate the alpha 1 and alpha 2, that is the short-term slope and the long-term slope. And this is a picture of DFA. For the signal-based feature, first we compute the first derivative and the second derivative of R intervals by Librosa package. And then we can use R intervals, first order derivative and the second order derivative to build a three-dimensional GNN model with 8 clusters. Here I set the number of cluster 8. And we can get the mean, covariance, and the weight from this GNN model. And then we can use the feature vector to encode a new feature. And this signal-based feature, I see it as the distribution the distribution in this GNN model. For the normalization, I apply two different normalizations. First, I use the baseline ECG signal as neutral emotion and compute the mean and standard deviation by the baseline ECG features. With the mean and standard deviation, we can apply the z-score normalization on our data person by person to eliminate the individual differences. And second, using the training set as basis and calculate the mean and standard deviation. And then we can apply the z-score on both training and testing set to make the training and testing data in the same scale. And it can help the machine. It can help our classifier to learn easier. For the machine learning approach, I apply two different kind of algorithm. The first one is SVM, and the second one is MLP, the multi-layer perceptron. I set the MLP only 4 layers because if I go deeper, it will not improve the result. So I just set it 4 layer. Well, here is the system flow for the functional-based feature extraction. First, we get the ECG signal and then do the preprocessing to denoise and detect the R peak and get the R intervals. And then we can calculate the 17 functional-based feature. And we do the normalization person by person to eliminate the individual differences. Here I use 10-fold cross-validation to separate training and testing set. And then do a normalization between training and testing to make all the data in the same scale. And finally, use the machine learning approach SVM and MLP as classifier to recognize the emotion. This is the system flow for the signal-based feature. We get R intervals and then we normalize it person by person. Use the baseline ECG signals R intervals, and then use the Librosa package to get the R interval, first order derivative and second order derivative. And then we use GNN model and the feature vector to get a new feature. Here I also use the 10-fold cross-validation to separate the training and testing set. And because the feature came from GNN and feature vector is kind of the distribution in the GNN model, so I think there is no reason we use the normalization on it. So here I don't use the normalization between the training and testing set, and then use multi-layer perceptron as my classifier to classify the emotion. For the evaluation, first is a result from SVM. Here we can see the improvement of normalizations can truly eliminate part of the individual differences. And the final result is 16.56% for arousal and 53.31% for variance. This is for functional-based feature. And second, for functional-based feature, the result from MLP, yes, and we can see that the accuracy is higher than SVM. Yes, if we compare these two pages, we can see the MLP is higher than the SPM, the result. Yes, and the improvement of normalization is still exists. The final accuracy is 61.12% for arousal and 57.69% for variance. And this is the evaluation of the signal-based feature. The result is from the MLP. And the final accuracy is 60.56% for arousal and 57.19% for variance. If we compared the signal-based feature and the functional-based feature, this is the functional-based feature, and we can see the differences of recognition accuracy between these two features is less than 1%, and it means that the signal-based feature may have the same ability of the functional-based feature. This is a comparison of my project and other works. Here I choose the research with released database because I think they are more credible. Dreamer is a database I use in this project, and the accuracy is about 62%. In the Dreamer, 71 features were extracted from ECG signals, and here I only extract 17 features. That is, if I can get more features, there is an opportunity to improve the accuracy. And generally speaking, the accuracy of arousal should be higher than the accuracy of variance because the because the physiological response is very easy to see when we become very active. The heartbeat will be faster and the blood pressure will be higher. And it is a surprise that DEAP can get the accuracy of variance higher than arousal. And for Dreamer and the DEAP, they separate the variance arousal into two levels. And for the MAH-NOB HCI, this research separate variance arousal into three levels. So all these works only get the accuracy that is higher than random guess, about 10 or 12 percentage. So in this comparison, we can know that emotion recognition through physiological signal is a very complex problem. In this project, I achieved the emotion recognition system with two types of feature extractions, and the accuracy of functional-based feature is 57.69% for variance and 61.12% for arousal. The accuracy of signal-based feature is 57.19% for variance and 60.56% for arousal. In this project, I proved that the normalization by baseline signal can eliminate part of the individual differences and improve the accuracy. Also, I proposed the signal-based feature that is rarely used on physiological signal analysis. But in the project, I also proved that the ability, it can have the same ability with the functional-based feature, which is very commonly used. And by the comparison with other works, we can see that the emotion recognition is a very complex problem. And I think the problem is because of how we elect our emotion. All these three works, they elect the subject's emotion by watching video clips. And I think it is very different from the real emotion, because emotion should be the interaction between people and people. But it still provide a way for us to do a research in this field. And then it's a demonstration. Here I installed three toolbox, the MHRV toolbox in MATLAB, and Librosa in Python, and VLFit in MATLAB. And in MATLAB, I do the preprocessing, the object detection, and the feature extraction. In Python, I roll the Librosa to get the first and second order derivative and the machine learning approach. Okay. So let's run the MATLAB code. Okay, and it takes time, and I will explain my code. First, just load the database and then separate each database by different subjects and the different emotions. This part is the wave-related noise. And this part is the object detection. We just set the different window size and then use the difference ratio. Yes, use the difference ratios to get the peak position. Here is a feature extraction, and I use some feature. I use the MHRV toolbox to get it. Yes, and then get the feature vectors. And here we after we get the R interval, we can apply the Librosa package to get the first and second order derivative. And here is we use the first order derivative, second order derivative, and the RR interval to build a three-dimensional data, and then run the GNN model to get the means, covariance, and the weights of the GNN model in different clusters, and use the feature vector to encode a new feature. And this part just how I turn the 5-level variance arousal into 2-level variance arousal. Here is I read the baseline ECG signal, and then do the noise, RP detection, and calculate the features, and then we can get the mean and standard deviation of the baseline features, and do the z-score normalization person by person. Yes. And this is we can use the baseline ECG R interval to do the normalization for the signal-based feature. Yes, and then we finish this code. We can do the Python code. We can get all the feature, and we can run a Python code. This is for SVM. This is the SVM for functional-based feature. And here I run the accuracy for 10 times and get the average. It will be more stable. Then I just run it one time. Yes, and here is I load the data, and I eliminate 3 subjects because for these subjects, some feature is like outlier. I cannot compute the feature. It will be outliers. Yes, and here I just run the arousal label. We can change it, or label A to label B, to run the variance. And here is I run the code 10 times and get the average, and use the 10-fold cross validation, and the accuracy is 59.66%. It will be a little bit different because we use the k-fold cross validation. It will separate it randomly, so separate the training and testing set randomly, but it will be very close. And next is the MLP for the functional-based feature. Here I also only run the arousal. And here is the structure of my multi-layer perceptron. I use 4-layer structures, and I have 16 features. And here is the code. This is the z-score normalization for the training and testing set, and the accuracy is 61.16%. And this is the multi-layer perceptron for the signal-based feature. Oh yeah, and I set the epoch equal to 10, the batch size equal to 32, and the learning rate equal to 0.001. And for the signal-based feature, because we set the cluster number of GNN equal to 8, and we will get 8 times 3 times 2 features after the feature vector, and the accuracy is 59.19%. It will be a little difference because of the 10-fold validations, and all the code I run it 10 times and get an average. Here we don't apply the training and testing normalization. Yes. So I think it is the end of my presentation, and thank you for your listening.